Hi everybody. So my name is Luca Biggio, and I'm a PhD student at ETH Zurich, and today I'm presenting bridging the Sim2real gap for long-term battery discharge predictions with time series transformer. And this is joint work with Tommaso Bendinelli, Professor Olga Fink, and Chetal Kulkarni. Batteries are key components of modern technologies and are going to be super important in the future to develop greener and more sustainable technologies. So the goal of our work can be phrased in this sentence, in this very simple sentence. So given an input current load profile, we want to predict the evolution of the voltage discharge curve associated with it. So this is an apparently very simple problem, but it can become very tricky because of the fact that batteries tend to degrade over time. And you can see the effect of this degradation in these two plots. So you see that by varying these two parameters, the capacity Q and the internal resistance R, the voltage discharge curve can change quite dramatically. And this makes the task of voltage prediction pretty hard to perform. So these two parameters, Q and R, the capacity and the resistance, are very highly correlated with the degradation of the battery. So, in order to tackle the problem of voltage discharge prediction and degradation inference, we developed a method that is based on two parts. In the first part, which we call the data generation process, essentially we use a simulator provided by NASA, which simulates the behavior of lithium-ion batteries. And in particular, it takes as input a current load profile and a pair of degradation parameters Q and R, and it generates a voltage discharge curve. We repeat this process multiple times in order to create a large data set and that we use for training our model. Our model consists of a transformer, a very popular model nowadays, especially in natural language processing, and it's divided in two parts. We have a transformer encoder and a transformers decoder. The transformers encoder takes as input the initial part of the current and voltage trajectory, and its role is to extract physics information about the degradation level of the battery. Once this information is extracted, we pass it through the decoder, which takes as input the embedding extracted from the encoder and the full current profile in order to predict the full voltage discharge curve. We compare this prediction with the ground truth, and we get a loss function term, which enable us to learn the parameters of the model. So here we present, Tommaso is going to present some results.
Yeah, thank you, Luca. So what we can see here is basically when we train and then test our model on synthetic data, we get really good performances. So I don't know if it's possible to see from there, but basically there is an orange dashed line that represents the ground truth, and the blue line represents the prediction. And they basically overlap, both in cases of rather simple current input profiles, such as the one on the top, but also in case where we have multiple transitions in the input current profiles. This means that basically our model has learned the physics that was in the simulator. Additionally, I want to stress out that these time series tend to be rather long, so they consist of thousands of time steps. And still we can perform good in those long time series. Then when we move to basically real data, when we deploy our method that was just trained on synthetic data on the real data set, our method is kind of suboptimal in the sense, let me show here, basically this is the prediction, the yellow line above, compared to the dashed line, which is the ground truth, you have this red area that represents the Sim2real gap. However, when we basically do a couple of fine-tuning iterations, we can reduce the Sim2real gap dramatically, and we get this pink line over here. And this pink line is much closer to the ground truth, meaning that our model has actually, after just a couple of iterations fine-tuning, learned the complexity of a real battery data. Overall, I want to conclude saying that our method can simultaneously infer the aging parameters of the battery and estimate the discharging point. And it's based on a transformer architecture that we tailor-made for the problem, because again, we have this long time series, we have to change a little the architecture, and can be applied as well on real battery data sets after fine-tuning. What we propose to conclude is a general framework that can then be applied also to other possible applications. Thank you very much.